Welcome to today's paper reading. Today's paper is titled, SoundStorm, Efficient Parallel Audio Generation. This paper was published on AR14 by Zalon Borsos and colleagues from Google Research. The SoundStorm model is designed for efficient, non-autoregressive audio generation. It leverages bidirectional attention and confidence-based parallel decoding to produce high-quality audio. Compared to the autoregressive approach of AudioLM, SoundStorm maintains the same audio quality while significantly improving voice and acoustic consistency. It is notably faster, generating 30 seconds of audio in just 0.5 seconds on a TPU-V4. This model also demonstrates the capability to synthesize longer audio sequences, such as natural dialogue segments, given appropriate inputs. SoundStorm is a method for efficient and high-quality audio generation. It relies on a bidirectional attention-based conformer architecture that is trained to predict masked audio tokens produced by SoundStream, given a conditioning signal such as semantic tokens from AudioLM. During inference, SoundStorm starts with all audio tokens masked and fills them in level by level over several iterations, predicting multiple tokens in parallel within each level. This approach allows SoundStorm to generate audio 2 orders of magnitude faster than AudioLM's hierarchical autoregressive acoustic generator, while maintaining matching quality and improving consistency in terms of speaker identity and acoustic conditions. Neural audio codecs have been developed to reconstruct high-quality audio at very low bit rates, enabling discrete modeling for a variety of audio signals. These codecs often employ a hierarchical sequence-to-sequence approach, such as in AudioLM, where high-level semantic tokens are generated as an intermediate representation. On the other hand, RVQ-aware architectures focus on reducing sequence length by summing embeddings corresponding to the same RVQ input frame. This approach is exemplified by models like AudioGen, which uses a transformer with separate heads for different RVQ levels. Additionally, parallel decoding schemes have been proposed to improve inference time and allow bidirectional non-causal attention, extending the iterative sampling scheme of mask-it to token sequences produced by residual quantization. Figure 1 illustrates the architecture and masking scheme used for training SoundStorm, a model designed for efficient parallel audio generation. The model reduces the input sequence length by summing up the embeddings of the tokens corresponding to the same SoundStream frame. During training, an RVQ level Q is sampled, and a subset of randomly sampled tokens at level Q are masked together with all tokens at RVQ levels Q+1, Q. The loss is computed only on the masked tokens at level Q. This approach allows the model to efficiently handle long audio sequences while maintaining high quality and consistency in generated audio. SoundStorm processes a sequence of discrete tokens representing the conditioning signal and generates a sequence of SoundStream tokens, which can be converted back to audio waveforms. The model architecture involves interleaving time-aligned conditioning tokens with SoundStream tokens, embedding the sequence, and passing it through a conformer. The output uses Q-dense layers to produce the target SoundStream tokens. The masking scheme for training and the iterative parallel decoding method are designed to respect the conditional dependencies between RVQ levels, allowing for efficient and high-quality audio generation. In the experiments, the model training setup involves using a SoundStream codec that operates at 50 frames per second and a bit rate of 6000 bps. Semantic tokens from W2V BERT embeddings are used for conditioning. The model architecture is a conformer with 350 million parameters and 12 layers. During inference, the RVQ decoding strategy includes 16 iterations for the first level and greedy selection for subsequent levels, requiring 27 forward passes to generate 30 seconds of audio. The model is trained on LibriLite, which contains 60,000 hours of speech data. Subjective evaluations focus on speech intelligibility measured by word error rate, WER, and character error rate, CER, audio quality assessed by a MOS estimator, and voice preservation evaluated through cosine similarity of speaker embeddings. Figure 2 illustrates the acoustic consistency between the prompt and the generated audio for the long split of LibriSpeech Test Clean. The shaded area represents the interquartile range, indicating the variability in acoustic consistency scores. SoundStorm demonstrates higher acoustic consistency compared to Audio LM, with less significant drift over time. This figure highlights the performance difference between the two models in maintaining acoustic consistency in long audio samples. Table 1 presents a detailed comparison of the intelligibility, audio quality, voice preservation, and acoustic consistency metrics between Audio LM's acoustic generator and SoundStorm. The metrics are reported separately for short, 4 to 10 seconds, medium, 10 to 20 seconds, and long, 20 to 30 seconds, segments of the Libri Speech Test Clean dataset. The results indicate that SoundStorm not only matches Audio LM in terms of audio quality, but also significantly outperforms it in speech intelligibility and acoustic consistency. Specifically, SoundStorm shows notable improvements in word error rate, WER, and character error rate, CR, across all segment lengths, demonstrating its superior performance in generating intelligible speech. Additionally, SoundStorm maintains high levels of acoustic consistency, ensuring that the generated audio remains consistent with the original prompt over extended periods. This comprehensive analysis highlights SoundStorm's capabilities in parallel audio generation, making it a strong contender in the field of efficient audio synthesis. The integration of SoundStorm with the text-to-semantic token model allows for the synthesis of high-quality, multi-turn dialogues lasting up to 30 seconds. This approach is similar to SpearTDS. The dataset used for training consists of approximately 100,000 hours of dialogue segmented into 30-second chunks. A 0.6b parameter BestRQ model was trained on this dataset to extract semantic tokens. The text-to-semantic token mapping is modeled using a BiT5 large transformer, which has 1.2b parameters and can perform inference in 1.4 seconds on a TPU-v4. Figure 3 illustrates the runtimes of SoundStream decoding, SoundStorm, and various stages of Audio LM on a TPU-v4. Notably, SoundStorm achieves a real-time factor of 0.017, significantly faster than Audio LM's acoustic generator, which is 2 orders of magnitude slower. Additionally, the semantic generation stage of Audio LM completes in 1.4 seconds, enabling the synthesis of 30 seconds of speech continuation within 2 seconds, including SoundStorm and SoundStream decoding times. Figure 4 illustrates the impact of varying the number of decoding iterations on the audio quality at the first RVQ level. The study reveals that employing 16 iterations results in a notable improvement of 0.1 to 0.2 in the quality score when compared to the level-wise greedy decoding method. This experiment was conducted using speaker-prompted data from the Libri Speech Test Clean dataset, highlighting the effectiveness of the 16-iteration strategy in enhancing audio quality. The SoundStorm model presented in this paper synthesizes high-quality audio efficiently from discrete conditioning tokens. It demonstrates 2 orders of magnitude faster performance and higher temporal consistency in generating long audio samples compared to the acoustic generator of Audio LM. By integrating with a text-to-semantic token model similar to SpearTDS, SoundStorm enables scaling text-to-speech synthesis to longer contexts and generating natural dialogues with multiple speaker turns, offering control over both speaker voices and content. The SoundStorm model is designed for high-quality and efficient generation of neural audio codec-derived representations of audio. It serves as a replacement for the acoustic generation pipeline in Audio LM and SpearTDS. However, the model's outputs may reflect biases present in the training data, such as specific accents and voice characteristics. While speaker characteristics can be controlled through prompting, a deeper analysis of the training data's limitations is planned for the future. The model's ability to mimic voices raises ethical concerns, including potential misuse for bypassing biometric identification and impersonation. To mitigate this, the generated audio has been verified to be detectable by a dedicated classifier with a 98.5% success rate. Future work will explore additional detection methods, such as audio watermarking, to ensure responsible use of this technology. In this section, the authors acknowledge the significant contributions of R. N. Jansen and R. J. Scarry-Ryan for their technical discussions and valuable feedback. Additionally, they thank Elena Anti-C, Brian McWilliams, and Paul Rubenstein for providing speech samples. The authors also express gratitude to Michael Dooley and other voice actor volunteers who donated their speech samples, which were crucial for the research. Thank you for watching.